So adding ordinates again, and the reason that I know to do that is because this is not a graph that I've really ever seen before. It's not like a standard graph. So what I'm going to do is try and make this into something that I recognise, and hopefully the addition of two things that I recognise. So I'm just going to write down the function. I'm going to split it up because it's both of the things on the top line are over that denominator. So x to the power of 4 over x squared plus 2 on x squared. And I know that I can cancel the powers down. So I now just have an x squared left there, which is awesome. And a 2 on x squared. Now we know the types of graphs here. This is your good old parabola. This one is the truncus and looks like, oops, the trunk of a tree, like that. Okay, and this has got that shape. So we know the basic shapes here. So our goal now is to try and find, as before, your asymptotes, vertical asymptotes and non-vertical asymptotes, intercepts and turning points. So the first thing I'm going to do is actually do a rough little graph of this, and I'll do this on this side. Oops, let's see if I've got, put it over here, do it in black. Okay, so we've got my graph here, and I'm going to put in different colours. So I'm going to do the x squared in green. An x squared is a parabola that just goes through the origin. Oops, and it should be fairly symmetrical. I'll try that again. Something like that. And we've got, I should label these as well. There's y, there's x. And then we have the truncus, which I'll do in purple. So that's got this kind of vibe. And you can see they're really rough sketches. Okay, I'm not doing anything, really exciting. But what that's helping me to see is what's going on here with these two graphs. Now, in terms of adding the ordinates, what we do is we look for any intersections and we then double those points. So it's this amount of distance again, that's where we'll have a new point. This amount of distance added to itself would be about there. We know that for the truncus, and I'll do that again because it doesn't look very close. And again, yours will look a bit better than what I can do on the tablet, but we've got a vertical asymptote at x equals 0. Oops. There we go. So I'm just going to put that there. And that you can see here is also given in the function. We know that x can't be 0. It's all the reals except for 0. So we have a vertical asymptote there. We also have a horizontal asymptote here as well for the truncus. It's a kind of behaviour line for that truncus. Okay. Now, in terms of what we're going to be dealing with here, you can see that we need to consider what happens as x gets really big. So as x approaches infinity, our function x squared is going to get really big. So that will approach infinity, get really big. This term, the 2 on x squared, that term is actually going to approach 0. So as x gets really big, our function actually starts to behave only like this part here, the x squared part. This part here becomes basically smaller and smaller and smaller and smaller until it disappears. That's what we call transient. It's a transient term. It disappears, approaches 0. And we know that because you can see how the graph is getting smaller and smaller and smaller as x gets bigger in both directions. There's x getting bigger. So one where, and I'll just negative infinity. So when we look at this, we know that the graph that we have as an addition of ordinates will start to behave like x squared. So this is what we call a non-vertical asymptote. So y equals x squared is actually going to be a non-vertical asymptote. So I'm going to put that in there. And that means that this asymptote here, the one that we have from the truncus, is actually not going to be applicable or necessary to our graph. So I'll just get rid of that. Oh, I'll do that on the next, when we do it again. So to finish off, we've got the vertical asymptote, we have the behaviour line. We need some intercepts as well. What I'm going to do is actually graph this now. I know that as we get in close to 0, see the green graph is starting to approach 0. It has no effect on this graph, but the purple graph gets massive. So this graph will actually start to behave like the purple graph, like that. Okay, and as x gets big, you can see here that the purple graph starts to be smaller and smaller and smaller, so it contributes less to the addition of ordinates. So our graph starts to behave like y equals x squared. So we've got two parts to the graph. The parts here, okay, and we've also got some turning points that we need to look at as well. Now you can see from the graph you're not going to have any x and y intercepts, so we don't need to worry about those, but we will have some turning points. So for the turning points, all we need to do is we need to find the derivative and set that to 0. So we have our function here. I'm just going to write down our function. F of x equals x squared plus, I'm going to write this as 2 times x to the minus 2. I'm just bringing it up. It's easier for me then to differentiate this to 2x minus 4x to the minus 3. And now what I'm going to do is set that derivative to 0. So I've got 2x minus 4 on x cubed equals 0. That implies that 2x equals 4 on x cubed. Oops. And that means that 2x to the power of 4, I'm just taking this up, multiplying it through, equals 4. And I'll go on to the next side here. I might leave that actually. Just go here. I'm just going to move this down because this is what we're still working on. And now we have 2x to the power of 4 equals 4. Well, dividing both sides of that by 2, we have x to the power of 4 equals 2. So therefore, oh, I've got a weird little 2 there. Therefore, x equals, now this is going to be the fourth root of 2, and it will be plus or minus the fourth root of 2. Okay, so fourth root of 2, I'm going to write like that. So if we're looking for values here of the graph, we've got our function f at the fourth root of 2. We would have fourth root of 2, and I'm actually going to write that differently as well so you can see it. It's 2 to the power of a quarter. It's actually a little bit easier to work with that way, so you can sort of see it more easily. 2 to the power of a quarter. So I'm going to put that 2 to the power of a quarter into here. I'm using the positive. So we've got 2 to the power of a quarter squared plus 2 over 2 to the power of a quarter squared. And I know that when I'm looking at powers across a bracket, they multiply together. So this would be a half, and this would be a half. 2 times a quarter is a half. So this is going to be 2 to the power of a half plus 2 on 2 to the power of a half. And I know, oops, let's do this in a different colour, that is equal to root 2 plus 2 on root 2. A little bit of simplifying will give you root 2 plus root 2 on 2. So multiply the top and the bottom by root 2 over 2. And you'll end up with 2 root 2. So you'll actually end up with, after all that work, when you put 2 to the power of a quarter in, you'll get 2 root 2. I'm just going to erase this section now. I can move that working up so we don't get confused. Oops. So that's our first turning point. And I'll actually do a better version of this graph, but I'll just put it here for now so we can see. This is for the positive here, so the fourth root of 2 to the power of a quarter. So this point here would be 2 to the power of a quarter and then 2 root 2 as its y value. And here, now by symmetry, I mean you can work this out with the negative here. You're actually going to find that you get, this is going to be the same value because the squaring will actually make this positive. So you'll actually get the same value, and by symmetry you know that makes sense because both of those points are at the same height. These are both symmetric graphs. So we have our two turning point values. They both happen at x equals plus or minus 2 to the power of a quarter, and they're here. So what we're going to do now is do our final graph, and I'll just erase this here so we can do our final graph underneath. So remember our turning points we found by letting the derivative equal 0. So our final graph, we'll do this one and we'll show all the asymptotic behaviour that we need to show as well as the turning points. And we don't really need much underneath because all the action's happening above. And so we've got y, x. Put in our asymptotes. You can see that the graph actually approaches two things here. It approaches your asymptote, your vertical asymptote. So we need to show that in our graph. So put that in. Vertical asymptote at x equals 0. Our graph also approaches this non-vertical asymptote that is x squared. So we need to put that asymptote in as well. So, and you can label that non-vert asymptote, y equals x. Then we need to put in our graph. Now we know that these points occur at the quarter root of 2. So I'm just going to put them in. I'm not even going to put a scale because it's quite small. Make sure they're at the same height. Our graph approaches both our asymptotes, like that. And I might just move this label, oops, just so that it's not in the way. Put it down there. And then to finish off, we need to make sure that we label our asymptotes, our turning points as well. So this was the quarter root, or the fourth root of 2, and 2 root 2 was the y coordinate, and this was the negative quarter root of 4 and 2 root 2, which was the y coordinate. So 2 turning points, no intercepts, and again, just being careful. I can see here that I didn't do that very well. Do that again. Just be careful that your graph approaches the asymptote but doesn't touch it. Okay, and that you're showing all of those turning points and any intercepts, and in this particular graph we don't have any intercepts. So our graph, x to the power of 4 plus 2 on x squared, is really just the addition of the two graphs, x squared, which is the parabola and turns into our non-vertical asymptote, and the truncus 2 on x squared. And you can see the resulting graph from addition of ordinates there in red.